This video, I'll show you how to calculate the torsional shear stress in a shaft. It's appropriate for what we're doing with our design because we also have a chain drive. So in this example, we have the driving sprocket here. So think about this being on your motor. In this case, we have a motor that has a torque of 200 inch-pounds counterclockwise. The diameter of the sprocket is 4 inches. As the sprocket rotates, it's going to pull on the chain with a force, which is going to cause the larger sprocket to rotate counterclockwise. Now, because the two sprockets are different size, the amount of torque is going to be different between this shaft and this shaft. So that's what we want to be able to calculate, is the torque in this driven shaft. In this case, we have a 10-inch diameter sprocket and a 1/2-inch diameter shaft. Before we do the calculations, let's look at a few of these items. One thing is design factor. So we'll need the design factor to verify whether our design is safe or not. For a dynamic load, which is what we have, the recommended design factor is between 2 and 4. Let's just use a 3 for our design factor. Let's talk about material type. So typically for shafting, you would use a 4140 type material. It's a chromoly steel. If we use one of these medium grade like OQT 1100, if we look at the yield strength there, it's 131 psi, so that's a good number for us. $131,000 psi. Other thing is case of T for stress concentration, because our shaft does have a keyway cut in it, and it's a profile key seat. We need to know what the case of T value is going to be. If you look at this chart, now KTS is for shear, which is what we have. The recommended value is that you use a 3. So if you come up here on this chart, you'll see with the key in place transmitting torque. So we'll just use a case of T equals 3. So as far as the calculation goes, first thing we want to do is calculate this value of force here based on the torque that we have. So if you look at the formula for torque, in this case, torque is going to be equal to force times the radius of the shaft, right? So torque is going to be transmitted from there to there and from there to there. So you're always going to use those radius values. Likewise over here, use that radius. So since we already know the torque, what we want to do is solve for the force. So force is going to be equal to the torque divided by radius. So let's start with our input over here. So what we have is 200 inch-pounds, and we have a 2-inch radius, so inches are going to cancel, and that's going to leave us with a force of 100 pounds. Now force needs to be in unit of pounds or newtons. We're going to go with English units of pounds. So that's the force that's going to be generated right here to pull on this chain. Now that's going to be transmitted through a different radius to create a torque there. So that's our driver. Let's look at our driven. Let's solve for torque. It's going to be force times radius. So that's going to be equal to 100 pounds. And in this case, it's a 10-inch diameter sprocket, so it's a 5-inch radius. So that's going to give us 500 pounds. Now you can write those inch pounds or pound inches. It doesn't matter. It's all the same. Let's see. So if we want to be consistent there, it's probably a good idea. So that's going to be the torque right there. So that shaft, that driven shaft, is going to feel 500 inch-pounds of torque. The next step is going to be to actually calculate the torsional shear stress using this formula, where T is torque, C is the radius of the shaft, K sub T is our stress concentration, J is that polar section modulus, which is a simple calculation based on the diameter. So let's solve for the torsional shear stress, again, on this driven shaft. So we know that torque is 500 inch-pounds. We just calculated that. The C value is our radius of our shaft, and we said it's a 1/2 inch diameter shaft. So that's going to be 0.25 inches. Case of T, we talked about that a second ago. We're going to use a 3, and that doesn't have a unit on it. And then we're going to divide that by the polar section modulus. So that's pi times the diameter of our shaft, which is 0.5. It's pi d to the 4th divided by 32. And let's see, when you do that math, it turns out to be 62,500 psi. So that's our actual stress, and it's a tau because it's a torsional shear stress. That's our actual stress that shaft right there is going to feel. The question we need to ask ourselves is this safe? So the next step is to take that number and compare it to our design stress. So our formula for design stress, now remember it's a shear, so it's a tau value. That formula is SY over 2N. We already said our N value we were going to use a N value equals to 3. So we looked up that yield strength. And that yield strength was 131,000 psi. We're divided by 2 times 3. Oops. Now it's going to be psi because the N value has no unit. And that leaves us with 833 psi. That's our design stress. So what we need to do to check and see if this design is safe is compare our design stress to our actual stress. Now, the design stress gives us the upper limit on the acceptable level of stress. So what we're looking for is, quite honestly, is that our actual stress is less than the design stress. So if we go back and look at our actual stress, that was 62,000, 500. And our design stress, which is 21,833, and we have a problem because our actual stress is greater than our design stress. So that's going to fail on us. So we can't use that. That's not going to work. So now we want to think about our options. What can we do to make this work? We're already using a pretty good piece of material. I think probably the obvious choice here is we need to increase the diameter of the driven shaft. What other things could we do? We could change the material, but then you may be getting into some kind of really exotic, very expensive, hard to get material. But that's an option, change the material. We could change the ratio. I'll call it a gear ratio, even though it's sprockets. But that's also going to change the speed and power of your vehicle. That may or may not be an option. A smaller motor. Again, that changes the performance of your vehicle. The other thing that's an issue is the fact that we got that keyway in there. So is there some other way to drive this without a keyway? And that's kind of tricky. Keyway is a standard way to transmit torsion. So again, those are options. I think our best option right now is to look at increasing the diameter of the shaft. So instead of using a 1/2 inch diameter shaft, let's try a 3/4. and see what happens. Now, this is an easy thing because all we got to do is recalculate that stress using different numbers. Now, the torque value stays the same. What's going to change here is, of course, our C value. So now we're going to go 2.375 inches for C. Remember, that's the radius. Case of T is going to stay the same at 3. Our J value is now going to change, so we'll recalculate J based on the 3/4 inch diameter. And what you get here is 18,145 PSI, so that's our actual stress. So now let's compare those two. So our actual stress is 18,145 PSI. Let's compare that to our design stress, which was 21,833 PSI. And what we're looking for is actual less than design, and we are good. So it's close, but it's not that close because remember we built in that design factor of 3 in there when we calculated design stress. So that's a good design. So what that means is I'd have to go back and I'd have to change the diameter. So change the diameter to a 3/4 inch instead of the 1/2 inch, and I'd have a good design on my hands. So that's the way you can do it. Just calculating the stress value doesn't do you any good if you don't go and check and see if it's going to be an acceptable level of stress for the material that you're making the part out of.